All right, so we use the indirect method to figure out whether an argument is logically valid or not, a deductive argument. Now we can use the indirect method to find out whether statements are consistent. Now we're dealing just with statements, not an actual argument. In dealing with validity and invalidity, we were dealing with an actual argument, something that had premises and a conclusion. And so in order to invalidate an argument, the conclusion must be false and the premises must be true. In this case, we aren't dealing with conclusions, we aren't dealing with arguments, we're just dealing with statements. And when we are looking at the statements, trying to figure out if they are logically consistent, what we are looking for is a situation in which both statements are true, or if there are three or four, where they are all true. And so if we were to fill out the entire table, we would just look for a line in which they are all true, because that's the definition of consistent statements, right? We talked about it earlier. When the main operators are all true on the same line, when we fill out the truth table, then we know we have a consistent, or that the statements are consistent. Well, if statements are only consistent when all truth values on one line are true, then why don't we just only look at the lines in which the values are true? Why don't we? So let's do that without having to fill out the entire thing. Let's try to create just the line in which both are true. Well, let's assume that they are true, because that's the only way that we can prove that the statements are consistent, by showing that they're all true. And so if we assume they are true and then try to force them to be true, but can't, then we know right away that it's inconsistent. Because if they were consistent, we could force them all to be true. So let's start with, well, we have two statements, P or Q, and then not P and not Q. Well, a disjunction has three possible ways to be true. And so if we were to start with this, we would have to go through each of the three possible ways that P or Q can be true, and then plug in the values for what we have for P and Q into here, and then look for the matching lines. In the case of a conjunction, there is only one way that it can be true. And so this is how we restrict ourselves to only one line. Because when we fill out the entire truth table, there will only be one line in which this is true. All the others are going to be false. And so we know that any line where it's false, it's going to be inconsistent, because it must be true to be consistent. All right, I must still be high because I'm really babbling on. Okay, the only way to make a conjunction true is for both its conjuncts to be true. So this is true, which means P is false and Q is false. The not operators are what make them true, and thus the entire statement true. So in order to make this statement true, P and Q must be false. So let's plug in P here. Let's plug in Q here. Now, what do we have? A conjunction in which both conjuncts are false, which results in a false truth value. And would you look at what we have here? A contradiction. That is what we're looking for in order to prove statements inconsistent. Sorry, I should say to prove statements not consistent. So if we were trying to prove them consistent, well, we failed. We now know that these two statements are not consistent, and that is how you use the indirect method, the shortcut method, whatever you want to call it, of discovering whether statements are consistent. All right, let's use the indirect method on statements that require that we fill out more than one line. When we have a conjunction or any statement in which the truth value can be true only one way, in the case where we have a conjunction as one of our statements, there's only one way that a conjunction can be true. And so we can get away with only filling out one line. But in the case where we don't have a conjunction, for example, here where we have disjunctions, disjunctions can be true three different ways. And so for us to prove this not consistent, if we're looking for inconsistency, we must show an inconsistency on every line. Because remember, for statements to be consistent, there only needs to be one line on the truth table in which all items, all main operators come out true. And so if let's go ahead and do that. Let's force this to be true. Well, there are three different ways for this to be true. Either both are true or one of the other is true. This is true or that is true. So let's start with true, true, which would make P false, right? And another way to make this true is to be true, false. That's I just have this memorized. That's how I know the three different ways. Anyway, so if this is false, that makes P true. And then the one other way in which to make it true is if J is false, then not P must be true, which makes P false. So these are the three different ways that a disjunction can be true. Now, since they're both disjunctions, we don't save any time by doing one over the other. So I just arbitrarily chose to fill out the truth table for the three possible ways that it could be true with this one instead of this one. There's no rhyme or reason to it. I just picked one because it's going to take the same amount of time. So now that we know the values, the three different possible values of J and P, in order to force this statement to be true, let's now try to force this statement to be true. Let us assume that it is. Let us assume that it is consistent. And let's see if it holds up. So J is true, which makes this false. And the only way to make this true is for X to then be true, right?